Hello. Let's continue. Last in the last video, there is ambiguity in the code. So let me clarify about ARIMA process. So we import the module here, ARIMA process and auto regression. And then assume that we already read the data to data frame called DA and extract the first column as X here. Actually, we already did that. So model is the X and we use three legs and trend C. So with constant. So about this part, seasonality false, old name false. So okay, about this part we would need some explanation. So this time let's use ChatGPT and then explain this code. This code model auto, yeah, X is the time series data and the leg 3 trend C, so it is constant. It includes a trend common in the model. The value C stands for constant, which the model will include a constant term. And the seasonal force. Okay, so yeah, there is no seasonality. We do not include seasonal component in the model. And the old name for this parameter control the naming convention for the model parameters. If set for is the new naming convention. Okay, in more recent version stat model. Okay, so there are further example. Okay, and then this one is interesting. So what options do we have? Okay, then it explains, yeah, trend, there is n, no trend or no intercept or constant. C is the constant term only. Yeah, and then T, we can maybe include linear trend. This is the constant and linear time trend. This is that both the intercepted term that increase linearly with time. Okay, CT, constant plus linear trend. Okay, so yeah, there are a couple of examples like this. So if you think there is a trend, you wanna include T or CT over here. Okay. So we fit the model M1. After we fitting model, we call it M1. And the coefficient for AR coefficient, yeah, they are the coefficient. Okay, but we add a 1 and we substitute minus in order to define characteristic function. So AR processor ARMA plus R AR coefficient like this. Create an instant ARMA with AR coefficient and then generate the characteristic function. So polynomial np numpy polynomial and then this coefficient which is basically this one, and then we print out characteristic function and we get the root and root of characteristic polynomial. Okay, so characteristic polynomial is 1 minus 0.3 x minus 0.18 x squared and something like that. And then we want to solve this one. It is third order polynomial, therefore it means there should be three solutions, so one real solution, natural, and then we have two imaginary solution. Okay, now we want to get the modulus in order to have a stable air process. The modulus, the all these solutions should be outside of unit circle. This is clearly outside of the unit circle. Okay, because we know it is a real number. This one are likely to outside unit circle because this is x-axis, this is y-axis. So basically both of them are greater than 1. So they are likely to be outside unit circle. So intuitively, it is certain that all those three solutions are outside the unit circle. But anyway, let's calculate modulus or absolute value of root. Then modulus is all 1.9, 1.9, 1.9. So they are all outside of unit circle, which means they are all greater than 1. Okay. How about K? Okay. Half time, the tenure, this is formula. And then we are gonna generate prediction. Okay. So model, this is same one. and the prediction is M2. Based on this one, we forecast for 8 step. Okay, so this is the prediction value. Okay, so let's move to the next example. Another example here. So let's increase the size. Another example. Monthly US unemployment rate from January 1984 to February 2015. I use this example to emphasize two messages. Simple model is often preferred. Seasonal adjustment does not necessarily remove all seasonality. Okay, so require quant mode. Okay, characteristics. Okay, so okay, so let's copy this one. Okay, up to this part, and then ChatGPT transform this R code to Python. Let me see whether ChatGPT is as excellent as Claude. Okay, to save R to Python, will you do Y Finance library? This is explanation. Let me try. Well, this is a bit, it looks inefficient, but let me try anyway. Code, and then error. Y Finance, yes, it does not work, so there is error. Okay, okay, so let me try alternative one. Let's go to Claude. I prefer Claude. Claude is usually better in code. So, well, again, copy. Okay, transform this R code to Python. Okay, let's try this one. Here's the Python you could provide the pandas data radar. Okay, PDR, PLT. Okay, copy code. Let me try. Okay, pandas data PDR. Fetch it on rate. Okay, so clearly Claude is better. Okay, so it's unemployment rate data. Okay, something like that. Okay, it is very recent data. Huge unemployment spike unemployment due to COVID-19. Okay, so well this one, and then okay, that's interesting. Date, rate, and then we can do other thing. Okay, and then let me try this one. Okay, and then copy. Autocorrect, excellent, excellent. Okay, so Claude is clearly better. Okay, in this way, again copy, and then paste. Okay, it generates solution. Okay, so you can do that. Oh, select there is error. MLE is not a valid estimator. Model fit, then we can simply delete this one. Okay, yeah, nice, great. It looks perfect. So anyway, in this way, you can now use either Cloud or ChatGPT. You can transform this R code. So anyway, this is R code unemployment rate, and then yeah, order cells and number of order here is 12. Well, it is intuitive. It is 12 months. Okay, it is unemployment rate, and then there's the monthly, uh, and then like yearly seasonality. So 12. We can include up to 12. The 12 order. That makes sense. One simple test, and t value is not significant. Ultra true mean is not equal to 0. So 95% interval, something like that. Okay. The M2 order 12. 1 0. And then we, as the ARIMA model, now we use 12 lag for every month. Okay. For every month, assuming the monthly pattern. Okay. Monthly pattern. So we have this one. Okay. So this is 12 AL coefficient. Okay. They look quite significant. Okay. All standard errors are very small. Some of them very small. They look quite significant. Some of them are quite significant. And then remove insignificant parameters, something like this. Well, here the usually rule is that when standard error is half of the coefficient, then usually it is significant. Okay, so yeah, like this way, warning message, and then yeah, ignore insignificant one here, coefficient, and then we do the prediction. Okay, frequency 1. Okay, so it is time series to aspect unemployment, and then M3 is laid again to 1 when now we include seasonality here, and then AR1 AR2 MA1, so seasonality, seasonal AR1 seasonal MA1, and then yeah, there is a solution, so we can skip it. Back testing for model comparison. Yes, so we do back test R, so backtest this one, error mean absolute error out of sample, backtest M3. So well, we compare the two model, backtest M2A model and M3 model. Well, which is better? Residual mean square, the smaller the better. So we can compare this one and this one. Okay, this is smaller. So this M3 model is better. How mean absolute? This one and this one. Again, this one is smaller, so we may conclude that this one is better. What is M3 model? Here M3 model is right. If we include two AR racks, one MA rack, which we are going to run, and then seasonality. Okay, seasonality with one rack and seasonality MA. Okay, seasonal error. Okay, we can seasonal AR model and seasonal MA model. Okay, so this one is slightly better. Okay, so by including seasonality over here, actually we can simplify the model. Okay, here there are a lot of coefficient like 12, well, but by including seasonality, and then we can make model simpler, and then it even performs better. Okay, now let's explain the moving average model. Model with finite memory. Some daily stock returns have minor serial correlation, and it can be modeled MAO AR model. So this is MA1 model, moving average model. For it, the stock return is well, some fixed part, mean drift plus error term, and then it is affected by previous error. Okay, so it's MA1 only error term. Use limited memory because it only one period before error affected. So in the previous AR1 model, we have RT minus one, right? We have something RT minus one. By including RT minus one, it is infinite memory. Okay, although it is decreasing. Now stationarity always stationarity because it does not depend. It depends only well one period limited past. So intuitively it is stationary. Okay. And the mean is something like this. Variance is this one. Autocovariance is that leg 1, this one, and leg L, L is greater than 1, it is 0. So RT minus L, there is 0. So it is limited memory. So RT is not related to RT minus 2, T minus 3. It is intuitive because only the previous error term, white noise effect, today is written over here, right? Autocorrelation function rho 1 is looks like this one. You can calculate it. Rho L greater than 1 is 0. So it is finite memory. MA1 model do not remember what happened 2 time period ago. This is the key difference from AR1 model. Now forecast model, one step further, R and 1 mu minus theta AN. Why? Because at time n, an is known, but an plus 1 is not. Okay? And then, so one step ahead forecast en1 is an plus 1 with variance sigma n. And then multi-period ahead r and l is simply mu. Okay? Because error term, today's error term does not affect, today's shock does not affect 2 period ahead, from 2 period ahead. So only mean part matter. Okay. Thus for an MA1 model, the multi-step ahead forecast is just the mean of the series Y because the model has memory of one time period. Now multi-step ahead forecast error is of course E and L is A and L minus theta A n plus L minus 1. Variance multi-step ahead forecast error would be something like this. Okay, because each A, okay, this A is sigma A square, variance sigma A square, so then square this, so we have theta square. Invertibility. This is basically called AR representation. Concept RT is proper linear combination AT and the past observation RT minus 1. Why it is important? It provides a simple way to obtain the shock AT. For an invertible model, the dependence of RT on RT minus L converges to 0 as L increases more, or L increases. So here condition is theta is less than 1. Okay. Invertibility of MA model is the dual property of stationarity of AR model. Okay. How about MA2 model? MA2 model is something like this. Here, so we are dependent 2 period ahead shock. So if we use a backshift operator, it's mu plus 1 0 1 b. There's b square. B a is a t minus 1 b square. A t is a t minus 2, right? Stationarity with ERT equal mu. Okay, clearly stationary because the distribution doesn't change. Mean and variance. And then ACF autocorrelation for the R rho 2 is not 0 but rho L. L is greater than 2 should be 0 intuitively because it depends on 2 period ahead, 2 period before shock. Okay, so it is longer than 2 period before. Okay, then the correlation should be 0. Forecast go to the mean after 2 period, right? Because today's shock affects only for the next 2 period. Building an MA model, specifically use sample autocorrelation function. So sample autocorrelation are small after leg Q for MAQ series. Okay, which means that after Q step, well, the correlation becomes 0, which is exact property of this one, right? Then it implies that maybe it is MAQ process. Constant term check the sample mean. Estimation use maximum technique called maximum likelihood estimation. Okay, of course we can do it code. Conditional assume AT is 0 and exact treat AT with T less than 0 as a parameter to estimate them to obtain likelihood function. Okay, exact model preferred it is often computing intensive. Okay, well we can simply use the default model in Python. Model checking examine error. Okay, so if MA model is right, it is sample same, the residual should be 0. Forecast use residual as AT to perform forecast. So model in R parameterized MAQ model, something like this. Okay, so MAQ model. Instead usual minus sign in theta. Consequently, care need to be exercised in writing the fitted MA model in R. For instance, theta hat minus 1 MA1 in R indicate the model is AT minus, well, 0.5 AT minus 1. Okay. So this is code. So okay, so again, well, it would be not so difficult to transform this one into Python. Okay, I won't do that because Claude or ChatGPT can do that. So here set working directory here, and then in our library take call fpage, and this is name of data. Okay, it is in our folder, and dimension of this one is it has, well, 10,194 row and 4 columns. Okay, and then we evaluate computer percentage log return of the evaluate index, third one, and we generate autocorrelation function with max 10, and then we M1 is ARIMA model with 001. Okay, fit this MA1 model in R. So MA1 fit is that something like this. So inter tabs and then MA1 parameter. Okay, sigma 2 estimate is 0.9905. Okay, something like this, and then predict for the next 5 period based on this model, and then yeah, this is the prediction. Okay, so next 5, only first one is different, but from second period they are all same because today's shock only affects this one, and then today's shock goes away from 2 period before. Of course this one will be affected by tomorrow shock, but we don't know tomorrow shock, right? That's standard error. Okay, standard errors are something like that. Okay, they should be same. Okay, only the first one would be different. Now we can mix AR1 AR model and MA model. This is mixed AR MA model. It's compatible for flexible model. Here we focus on ARMA 11 model for simplicity, useful to understand Garch model later on. So ARMA 11 model is 1 minus theta 1 backshot RT 501 minus theta BAT, like this one. So, well, BRT is RT minus BAT, AT minus, so we solve it and it looks like this. So RT is 5 1, RT minus 1, 50, AT minus theta 1, AT minus 1. So a combination of AR1 model in left hand side. So this is AR1 model and MAO model. Okay, this one, right hand side. So stationarity is same as AR1 model. Invertibility same as MA1 model. So mean of AR model is this one. Okay, you can put expectation of RT minus RT and expectation RT minus should be same. Expectation of A and expected AT minus they should be zero. So if we solve it, we have this one. Variance, well, we can calculate it. The autocorrelation function satisfies rho k is set at rho k minus of k equal 1, but well, this is something like this. It is not theta 1 because we have MA1 parameter. This is the difference with the AR1 model, ARMA 11 model. Partial autocorrelate does not cut off at finite lag because we have AR model. Now building on ARMA 11 model, specification use EACF and AIC. What is EACF? How to use it? Well, we can see the text here 9. And estimation conditional exact likelihood method. We can use code model checking it before and forecast MAO affect one step wide forecast others are similar to those AR model. Okay. The three model representations AR MA form compact usefully in estimation and forecasting. AR application by long division destruct this. It tests how RT depends on its past values. MA represented by a long division. It looks like this one. It has how RT depends on the past shocks only. So it is depends on its own value. It is shock. For a stationary series, all psi I converges to 0 as I become infinity. Okay. Thus, the effect of any shock is transitory. It does not have significant effect forever. It should decay, go away in the long run. Otherwise, the process is not stationary. Okay, it is unstable, meaning that its distribution change over time. Okay, then we cannot make estimation. Distribute itself, process itself should be stationary, should come from same distribution. Okay, as far as psi comes to zero, so long ago that history does not affect today's one. Okay, as far as it does not accumulate, well, the process stationary. The MA presentation is particularly useful in computing variance of forecast error. Okay. For L step ahead forecast, the forecast error would be something like this with MA representation. Then the variance of forecast is simply this one. Okay, next unit root non-stationarity. Okay, here we have very famous model which is popular for two modern stock price. Here form is PT today's stock price, yesterday's stock price plus some noise. So it is random walk. This kind of process called random walk. Unit root it is AR model with coefficient is basically 1. Okay, but it is non-stationary because this is 1 in AR1 model. To make it stationary, well, this one should be absolutely should be less than 1, but it is now exactly 1, so it is non-stationary. Unit why? Because the various RT diverge infinite as t increase, because this shock accumulate, it does not decay. Okay, it keep accumulating. Strong memory sample autocorrect approach 1 for any finite lag. So repeated substitute shows that PT is some of the distance, so where this is 1 for all I. So we are keep adding the error term. So it is not surprising that error variance explode. As variance explode over time, where it means distribution change, we can make reasonable estimation here. Thus, psi does not converge to zero. The effective any shock is now here the permanent. Any shock here, because we are some demon, any shock to the process has a permanent effect. Now, random walk with threshold. Now we can add the constant term here. Okay, here mu is not zero. Okay, so we keep adding this shock, but we also add some constant term. This one is also called this kind of process also unit root. Any AR model with the AR coefficient which is 1 has 1, then it's unit root. Again, it's not stationary. It has strongman has a time trend with slope mu. Why? Because we are keep adding mu in every period. So mu constant number is, we have two accumulate. This constant number is accumulated over time, and this error term is also become stacked. So how to estimate this one? Okay, we need to take into account this non-stationarity. We have to make it stationary, otherwise we cannot estimate. One technique is differencing. One first difference, so RT, PT, T minus 1. If PT is log price, then the first difference is simply the log of return. Typically, the first difference means the change or increment to original series. That's why in finance, we prefer modeling return instead of level stock price itself, because stock price is random walk. It is not stable. Alternatively, it is the possible seasonal difference, where S is the periodicity. S4 quarterly series, S12 is monthly series. If a PT denotes quarterly earning, or then what is the change in earning from the same quarter 1 year before. Okay. So meaning of the constant inner model in MA model is mean, AR model is related to mean somehow. Okay. First difference is time slope. Okay. Practical implication of financial time series. Okay. Monthly log interval general electric is sample mean is the standard error is 0.26. Okay. Very significant. It's about 12.45% a year. Well, now G is very bad, but this time, at least for this period, G was very good. So one investment in the beginning of 1926 is worth annual compounded payment is like this one, huge. Quarterly compound and then continual compound should be huge. Now unit root test. Let PT be the log price of the asset. To test whether PT is not predictable or has a unit root, two models are commonly employed. Okay, PT is phi 1 PT minus 1 ET, and PT is phi 0 phi 1 PT minus 1. Okay, and we want to know hypothesis whether this is 1 or less than 1. If it is 1, then it is a unit root process. It is not stationary, unstable. Okay, it less than 1 is stable process. There is an interesting test called the Dickey flow test. Dickey flow test is the usual T ratio of the OLS level of theta phi 1 being 1. This is DF unit root test. The T ratio, however, has a non-station limiting distribution. Okay, so let delta P, PT is PT minus 1, then the augmented Dickey flow unit test for AR P model is based on this one. Okay, T ratio of OLS beta is the augmented Dickey flow unit root test statistic. Again, the test has a non-stationary limiting distribution. Okay, but that's fine. Okay, that's fine, because in Python or code, if we learn it, they take into account this non-stationary limiting distribution, and then we tell it whether it's unit root or not. Okay, example. Okay, example. Let's take a look at the example. Okay, consider log series US quarterly real GDP series from 1941 to 2008. Okay, data from Federal Reserve Bank of St. Louis. Okay, QGDPC96 TXC on the course web. So I think we can do it. Okay, this one is important. Unit root test is important in finance, so let's do that. So okay, we can go here, and then now we have to upload the data. Let's upload the data. So what is the name of the data? It is QGDPC986. QGDPC986. So Yeah, QGDPC96. I uploaded this one. And then next, okay, okay, code cloud, okay, to perform unit load test, and then wonderful, okay. Well, this is amazing, okay. Actually, it predict this cloud, this AI predict what I'm trying to do in future, okay. So anyway, let's paste it because this is useful. Okay, let me close it and then code. Hmm. So okay, so here I can read the DA. So well, yeah, it has single. Yeah, okay. So this one, no, this part is wrong. This part is wrong. We should take into account. Okay, between columns. Okay, so well, delimiter. Okay, amazing. It does everything again. Okay, delimiter. Okay, we actually we only did this part. Then if we run it, huh? Still it is wrong. Hmm. So let's see the GDP. Wow. So so here in read table, ignore what? Ignore NAN. Hmm. Let me see whether it works. Huh. Right. Still it does not work. GDP. Yeah. It does not work. So, mm, I think I have to check the data again. Maybe there is a data issue. Okay, so hmm, delimiter. Let me instead of this one. Okay, delimiter white space true. Okay, now it works. Okay, it works. So GDP data. Okay, something like this. Good. Okay. So here, okay, we read the GDP data. Okay, and then we take log of the GDP. Okay, delimit white space. Okay, this part is important here. Okay, and then perform augmented decay flow test. Augmented decay flow test, ADF result. Save it as ADF result and augmented decay flow test. Test statistic is ADF result 0. P-value and critical value. For key value in ADF341, okay, we print out this one. So, okay, augmented decay flow test state minus 1.8. P-value is this one, so it is not significant. Critical value 1.5 to 10% should be something like this. Okay, so here this is not significant. Okay, and then how about this one? How about perform? Well, this is the Phillips Shin, Schmidt Shin KPSS test, another popular one. Okay, and then we do KPS test and then test is 2.4, p-value for 0.1. So here p-value this one is significant here. So well, two tests generate different result. Okay, different result. So if we use this one, and it is significant, and well, if we decay augment decay flow, it is not significant, and then if it's KPSS, it is significant. Okay, let's test. So here, reg order 4. Here, well, the reg 4. Okay, well, we didn't take a reg 4. Here, reg 4 decay flow test p 또 cannot reject null hypothesis unit load. So if we cannot reject null hypothesis unit, so it is unit load. Or more careful analysis, difference of GDP. Okay, and then AR model, and then AR1 to 3, AR3 for different data confirmed. Okay, so let's do this one. So very interesting. Okay, so to add emerging file series. Okay, so copy code. So we take difference of the GDP and the reg, and then reg is what? Reg is none. Okay, automatically. So always there is the okay, so let me say just results. Okay, order of the AR model. So well, hmm. Okay, so well, this is not pretty. rec 3. Okay, let's find rec 3 here. How about we use 3 rec? Okay, 3 rec, then where rec 1, this one is significant, so we have 2 recs are significant. AR model, AR1 imagery modulus, so those modulus are all greater than 1, so they are modulus greater than 1, so they are fine. Okay, they are stable. Okay, and then we have at least 2 legs over here. Okay, so well, the correct way here, the correct way to model the GDP here is actually AR2 model. Of course, once we difference the process, first of course we difference it, so we can difference the GDP, log GDP. Here we take a log, right? So where percentage change to log GDP change is the log GDP change is will log, so it is a growth rate of GDP. So instead of modeling, so in order to estimate GDP, so the implication instead of estimate GDP, we have to estimate the growth rate of GDP, growth of the GDP, economic growth. And when we estimate economic growth of GDP, well, AR2 model will be possible here. How about ARMA 1 model for the X? Okay, so AR1, okay, the difference. Today it is a bit slow. So copy code here. So AR1 MA, well, so clearly, yeah, where MA parameter is not significant here. Okay, so here we include two, two, ARMA 2 1 model, ARMA 2 1 model, and non-stationary starting. Okay, huh? Auto rec. Maybe we wanna remove this one. Then it should be same to previous one. Yes, it becomes same to the previous one. Okay, so once we include MA parameter, it becomes problematic. Yeah, non-invertible because MA parameter will see. Yeah, this is well, it becomes non-invertible. Okay, non-invertible, so it is not good. So we want to remove this one. Okay. Yeah. So 0. Okay, and then 0. Or alternatively, okay, so alternatively, what I can do is code, and then instead of differencing, I use GDP. Then there is a unit root process. Then I can include 1 over here. Okay, then well, there is unit root, and then parameter is basically uh, or the one model. So yeah, again, this is significant. Okay, because I take into account here the unit root part. Okay, the question is slightly different over here. Okay, out product gradient complex step. Okay, so this alternative one. So I can include this one at the explicitly model is difference one over here. ARIMA process. Okay. So here coefficient 3. So R3 for the different data is confirmed. Now the command on R dealing with the constant if there is any difference, no constant use. The subcommand include min t in area command. Fixing some parameters use subcommand fixing ARIMA used unimplemented series as an example. Okay. Now exponential smoothing approach. Suppose available data is rt minus 1, rt minus, and we are interested in predict rt plus 1. Intuition is that data rt should be more relevant than rt minus in predict rt plus 1, right? Because rt is close to rt plus in terms of time. Similarly, rt minus 1 is more relevant than rt minus 2, etc. So importance is decaying over time. Okay. So a simple formula is that suppose we assign weight w to rt, weight w theta with theta between 0 and 1 to rt minus 1, weight w theta square to the data rt minus etc. That is, we use the initial weight w and the discounting factor theta. Simple fact, the weight must be summed to 1y, not to change the scale, not to change the scale. Therefore, 1 equal, well, omega plus, sorry, w theta squared, something like this one. Then we collect this together, w1 plus theta and w1 minus theta. Therefore, w should be 1 minus theta. Consequently, the one step ahead prediction of rt plus 1 should be, okay, r1 should be something like this, okay, by using this one. And then let a t plus 1 be the forecast error or the innovation at time t plus 1. Then we have rt plus 1 equal rt1 plus at plus 1. Okay, this is something forecasting error, difference between our estimate, which is this one. Okay, and then this one. Now suppose we have data rt minus 1, rt minus 2, and are interested in forecasting rt at time t minus 1. The same argument shows that rt minus 1 is should be something like this one. Okay, same. Now using equation 2 over here. Okay, now it is interesting. We have rt1 is this one, but we can put theta outside and collect this together. Then r1 one period ahead error is the previous prediction and then weighted average of the previous prediction and then today's observation, right? Intuitively putting the prior result into equation 3, now we have this one. Okay, rt plus 1 is this one. Again, weighted average of today's observation and then historical estimate, and then we have error term. Okay, but then, right, then rt minus theta rt minus 1 is another error term, a t. So it looks like this: rt minus theta a t plus a t plus 1. In the above, we have rt minus 1 plus a t. Consequently, exponential smoothing model is basically something like this. Okay, which is ARIMA 011 model. Okay, because here we have unit root in front of this weird one, and it can be written as 1 minus BRT is 1 minus theta BAT. This shows that exponential smoothing model is simply using ARIMA 011 model with positive theta, which is a discounting factor. Now we have updating rule for a given discounting factor theta. Now it is easy to update the forecast via exponential smoothing method because well our prediction is weighted average of today's observation and then in some sense historical average, the past prediction, long-term prediction. Okay, which means the new prediction is simply the weighted average of the new data RT and the previous forecast, which is accumulated history RT minus 1. The weights are simply the initial weight and the discounted factor respectively because 1 minus theta is the initial weight.